For the sample size determination, first is the determination for one population, and this is the proof of the formula, which is a little messy. So instead of going to all this, we just remember that we need to use this formula to compute the number of sample. And in this formula, you can see that it has to be mu zero. It has to have mu zero, mu prime, sigma, z alpha, z beta, and so on. For the sample size determination, let's take a look at this example. This graph, we know that the average of something will be, we have normal distribution or t-distribution with a shape like this. If the mean is 368, we can assign the critical value here to decide whether it is it has the mean around 368 or not. The sample size has the mean around 368 or not. And we also have another type of error, which is beta. The beta can happen when the mean is not exactly the same as we hypothesize. For example, the real mean is probably something like this. Okay, so let's make it 405. So if the mean is 405, if we reject this, right? If our sample we fall in this region, we're gonna accept it, right? We're gonna accept that the mean is 368, but it is not. If the real mean is 405, if we accept it, we're gonna commit type 2 error, right? So this is the type 2 error. This is the probability of type 2 error. Okay, and we call it beta. So this is alpha. Okay, so the number of sample size is depend on the size of alpha and beta that we want to have. Theoretically, we want to have small alpha and also small beta to reduce the chance to have type 2 and type 1 error. Okay, how can the number of sample related to the size of this? Let's move on to the next slide, and we will eventually see it. So this is the formula to compute beta as a function of mu prime, and mu prime in this case is this. This is mu prime. This is mu prime, and this is mu. So mu is our hypothesized mean, and mu prime is actually the real mean. So the beta can be written as a function of the real mean, and we have this formula, And from this formula, we can compute the number of sample that will give us Z alpha and Z beta as we want. And also we have to have this standard deviation and hypothesized mean and real mean, okay, as a parameter to compute number of samples. So in order to have Z alpha and Z beta, we have to specify alpha and beta, okay. So let's take a look at as example here. So in one experiment, the hypothesized mean mu is 20, but the alternative hypothesis is mean greater than 20. Okay, with the random sample of 16 from the population with normal distribution and has standard deviation of 1.5. The experiment is conducted at 0.01 level of significance. What is the probability of error type 2 if mu prime is 21? Okay, so we know the formula to compute mu prime, to compute a beta from mu prime, which is this one. This is the one-tailed test, so we use this formula and just plug in the number. Okay, we get mu beta equal to 0.3669, which is quite a lot. It's about 37%. So the scientists want to reduce the beta to 0.1. So what happened is, if we plug in the number in this formula, in the formula to compute n here, we get number equal to 29.32, which is higher. So it means that the higher number of n will lower the error probability. So let's take a look at the graph here. Okay, so I plot the graph with sample size of 16. Okay, sample size of 16, and the hypothesized mean is 20, and the hypothesized standard deviation of sample. Okay, this is sample, so it's going to be 1.5 divided by square root of sample size, right? So it's going to be square root of 16, and then the real mean is 21. The real standard deviation is also 1.5. Okay, so I plot this, I get this distribution. The distribution, the blue distribution is the distribution of hypothesized mean, and the orange distribution is the distribution of the average of the sample, the real average of the mean, okay, which is 11 point, around 11. Okay, so you can see that with this, if we copy it, if we copy this image and then put it over in the Excel, okay, and compute the alpha for a little bit. If alpha is 0.01, okay, our critical region is gonna be what? critical region is we want alpha to be norm dot inverse, right? Probability is going to be 1 minus 0.01. That's it. Don't have to divide it by 2. And the mean is 20. The standard deviation is 1.5. Okay, so oh no, the standard deviation is it's got to be 1.5 divided by square root of n, and n is 16 here. Okay, so it's 20.8. Okay, so let's assume that this is 20.8. So what is the error type 2? Error type 2 will be from this critical value, draw this line up, and then it's going to be this area. The area under the curve, the real curve, so this is beta and this is alpha. So from the calculation we know that beta is about what? Beta is about 0.3667, which is very very high. It's more than 1/3 of the whole probability. So we want to reduce this. Okay, so I'm gonna plot the graph again with the sample size of 30. Okay. Now let's compute the alpha again. The set alpha. So set alpha, instead of this 20, we have to change this one from 16 to 30 number of samples. So with the new number of sample, alpha set alpha is gonna be 20.6. Okay, 20.6 is around, it's gonna be around here, right? So basically it's gonna be the same size as the left graph, but you can see that what reduced is the size of beta, right? Because what? Because the standard deviation, the spread of distribution, the real distribution and the hypothesized distribution is much narrower. Because the space is smaller, it makes the error type 2 smaller too. So the new beta, this one is around 0.1. And that's it. Okay, that calculating sample size is a little bit time consuming to do that by hand. So I will use the software to do that, and the software called G-Power. You can download this software by just type G-Power statistics software in Google, and then it will go to the download page, and you can download and install it in your PC or Mac. Okay, so this program will help you to identify number of samples very easy. So let's take a look at this example. Okay, so with this example, it's gonna be the mean difference between two independent means, and we just select the first one. This one will find the effect size, the sample size, required sample size for your hypothesis testing. The first thing is you need to specify the type 1 error. Type 1 error in this case is 0.01, right? And type 2 error, which is beta, sometimes they use power instead of beta. The power is just 1 minus beta. So if our beta is 0.1, power is 1 minus 0.1, which is 0.9. And the allocation ratio is like number of samples 2 divided by sample 1, which is 1 in this case because number of samples are the same. The effect size D here can be determined by hitting this button, and it will show the calculation box, and then you have to specify the mean of the first group, which is 20, and the mean of the second group is 21. The standard deviation of the first group is 1.5, the same as the standard deviation of the second group, which is also 1.5. So we can calculate the effect size D, which is 0.666667. So we copy that and put it in here, and then we hit calculate button. Okay. So for the biscuit example, it is one population, one sample case. Which is this one mean different from the constant. Okay, and we use a priori to compute required sample size given alpha, power, and effect size. It is one tail test. So we want to first enter alpha, which is 0.01 in this case. Beta here is actually they use power instead of beta, and power of the test is actually just 1 minus beta. If our beta is 0.1, power is 1 minus 0.1, which is 0.9. The effect size, that is the way to calculate the effect size D by click on this determine button. And in this determine button, okay, I have to delete this. We just enter the mean of the sample 1 and the mean of the population, the mean of population 1 and the mean of population 2, and the standard deviation, which is 1.5. Okay, so we can calculate the effect size D by hit this calculation button, and then we hit transfer to the main window. Okay, so 6.66667 is here already, and then we can hit calculate to compute the sample size. Okay, by this program, we got the sample size equal to 33, which is a little bit more than we got from the manual one. I think because the manual one assumed to have normal distribution, but this one assumed to be t distribution. That's why the number of sample size is a little bit greater. But you can see that this is very convenient. If you want to calculate the sample size, just use G-Power software. The sample size of two populations, the formula to calculate is even more complex. And so this is the formula to compute in case that m and n are the same. If m and n are not the same, it will be even more difficult than this. So instead of doing that, we'll just use G-Power software to do it. So let's go to the example, the soda example. So in this case, we already have that alpha equal to 0.05, but we don't know beta yet. Okay, but whatever the beta now is, we want to reduce it to 0.1. So what is the sample size for that? Okay, so we go to this example, soda example. Okay, and okay, we have the average and the standard deviation here. So we go to G-Power and select mean difference between two independent means, two groups. Okay, and we use a priori. Okay, and the error type 1 is going to be 0.05. Error type 2, 1 minus 0.1, 1 minus error type 2, 1 minus beta is going to be 0.9. And the allocation ratio, let's make number of samples from two populations the same, so it's gonna be 1. And then we have to determine the effect size, so we put the mean of the first population here, the mean of the second population in here, the mean of the standard deviation of the first population in here, the standard deviation of the second population in here. So we can calculate and transfer to the main window. Our effect size D is 1.35, and if we hit calculate, and the total sample size that we need is 26, and the sample size for group 1 is 13, sample size for group 2 is also 13. Okay, so this is how we calculate the sample size for two population tests.